Okay, guys, we are on 4.2 and we are going to start talking about Newton's laws. Now we start with Newton's second law. He obviously did them in order of 1, 2, 3, but we typically talk about the second law first because we kind of need it in order to understand the first and the third and how those work and kind of even what they mean by a force. So we're going to go into now, the rest of this unit is going to be focusing on types of forces and how they work and what they do to us, how do they make us move, stuff like that. So this is Newton's second law. A net force applied to an object results in the acceleration of that object. So if I'm pushing something, it's going to cause that object to accelerate. Now again, be careful you understand what this means. Acceleration means it's going to be changing velocity. It doesn't mean that it just moves, right? Because, and a lot of you guys got confused on this on your test, if I am moving at a constant velocity, that means I don't have any acceleration. I have zero acceleration if I am moving at a constant velocity. So this specifically means a force, a net force, which again, we're going to talk about what in the world that means and why it's in bold, causes something to speed up, to accelerate, not just move, but to move faster and faster and faster. That's what we're talking about here. Acceleration means your velocity is going to speed up or slow down. It's going to change. So as a formula, this is F equals ma. You may have seen this before. You probably have learned this in earlier years, but this is force equals mass times acceleration. That's what that is right there. And this is, again, the formula. The mass of the object, again, is going to be accelerating at a certain rate, and that's how we measure the force acting upon that object. It's mass times its acceleration. The greater the acceleration, the greater the force being put on my object. So what is a force even? Let's talk about that. So a force is a push or a pull. It can be either. So it can either be going in this direction or I can be pulling something backwards. Like if I want to pull my desk or I want to push it, those are forces. We have contact and non-contact forces though, because, right, again, pushing and pulling with my hands, that's a contact force. I'm having to actually touch it in order to apply that force. However, we have non-contact forces like gravity. Gravity isn't touching us, right? It's not contacting us. It's not in contact with us, but it is a force acting on us. So again, we have contact. You actually have to be able to be touching for that force to be applied. And then we have non-contact, which is just things that are always acting on us, even though they're not touching us. Forces are not energy. We're going to learn about energy later. Force is literally just, again, what's something acting on an object. We're going to be learning about energy later. It's not quite the same thing. Now, force as a quantity is a vector. It has magnitude and direction because, again, with my little Totoro here, if I'm applying a certain magnitude of force, well, I could be applying that same magnitude from various directions, right? So it really is very important which direction our force is coming from, because that's going to change the motion of my object, right? So force is a vector. Not only does it tell us how hard we're pushing something or pulling something, it also will tell us which direction. So again, this might be like a positive force. This could be like a negative force. We're going to talk about that later. Now, the units of forces. These are measured in newtons. We say 1N, right? So one unit of force is 1N. And we're going to talk a little bit about Isaac Newton. That name should sound familiar. But that's what we measure these in. So if I say, how much force was applied to this object, I would go 40 newtons or something like that. Just in the same way that we say, what's the mass of this object? Oh, it's 5 kilograms. The unit of measurement for force is newtons. Now, what this is equal to is kind of weird. I'm going to explain what this is. The way they write this is a couple different ways. This is 1 kilogram meters per second squared. So, whoops, sorry. Didn't mean to be transparent there. Did I go transparent? Full screen, there we go. Okay, so another way you might see this, and what it really is kilograms times meters per second squared. So a lot of times they leave the multiplication out and they just do kgm, but that's kilograms times meters per second squared, and that makes sense because if I look up here to my formula, mass is measured in kilograms, acceleration is measured in meters per second squared. So that's why these are the units for force. The name of this weird unit is called a newton. So you're not going to use this. You're going to say newtons instead. As we start getting into a lot of different types of things you never had to work with before that are kind of weird, we have different units like a joule, which is kind of a combination of a bunch of other small units. Like a newton is a combination of kilograms, meters, and seconds. Joules, same thing. It's going to be a combination of kilograms, meters, and seconds, but it's just kind of a weird combination, and so we give it a new name, so we don't have to write this every single time. We just have to write N for newtons. Okay, lastly, kind of giving us the background information here for forces. The variable is F, and often it has a little subscript for what type of force it is. So we're going to talk about that by the end of this video. But for example, the force of gravity, we put F with the subscript of G. Yeah. And we're going to talk more, like I said, about lots of different types of forces. There's 5 main ones that we're going to be focusing on right now. Okay, so let's go back to what we were talking about Newton's second law, that we're using the term net force. Now, if you have a net anything, hopefully you guys know that that means kind of after comparing like your positives and your negatives, right? If you're talking about your net pay for your paycheck, that's your pay after all your taxes are taken out, right? We have gross pay, which is before taxes, and then net pay is after taxes are taken out. So when we're talking about a net force, we specifically mean taking into account if we have some positive forces and some negative forces, what is the actual direction of the net force? Kind of what's left over. If I'm pushing in this way and pushing in this way, what's actually going on there? So here's a net force. It is the sum of all forces acting on an object, usually done in each component. We've been practicing that, yeah? So net, again, is specifically referring to this, the sum. Now, the reason why we say sum, even though, again, it's possible to have negative forces, is specifically because of that. I can have some positive forces, I can have some negative forces. If I add them all together, it's possible that I have a net force of 0. Looking at this example here, here's why we have to say net force. Say that both of these guys are not paying attention to the other and are just like pushing against the box. They're trying to move it, but they're both pushing this way because they're just idiots. They're just pure idiots. This guy is applying a force this direction. This guy is applying the same force in the opposite direction. Remember, guys, this is something you have to start getting an understanding of. Directions matter. If I have one arrow, if I'm going this way positive, the opposite way, I have to. You cannot just skip it. I have to designate it as a negative. So these two idiots are just pushing on a box with the exact same amount of force because they're not paying attention to what the other is doing. What's going to happen here, a positive force minus the same force, so that's, I'm just combining them, right? Plus F plus a minus F, yeah, if I want to write it like that so it makes sense, plus a minus F. This results in a net force of 0. So what do you think is going to happen to the box? It's not going to go anywhere, right? Even though they're both applying a force to this box, since they're applying the same force in opposite directions, we got a net force of 0. The box isn't going anywhere, right? So that's what we mean by net force. Even though forces are acting on this box, our net force is 0. So this box is not going to accelerate. We only accelerate if we have a net force. And again, this would be a case where this box isn't going to be moving at all. It's not going to have any acceleration. So let's go ahead and write this first part down, and then we'll talk about the second part. So when the sum of forces equals 0, again, these two idiots pushing up against the box, we don't have any acceleration. The box isn't going to move. Let's talk about the second part. What happens if there is a net force? Not balanced. Again, same but opposite means balanced, right? So if there is a net force, let's look at this example instead. Let's say these guys stopped being idiots and finally were like, oh, one of us should push and one of us should pull. And then they realize what they should do. So let's say this guy is pushing with a force in this direction, and this guy is pulling. So now he's pulling with the same force, but now it's a pull, so it happens to be in the same direction as the push. That should make sense. What is this net force? Well, we have the guy pushing with the force of F. We have the other guy pushing with the force of F. This results in a force this direction to F. It's going to have twice the amount of force if we just had one guy pushing or pulling. So what's going to happen is that's the direction of my motion. That's the direction of my acceleration, because that's the direction the net force is in. So if we do have a net force, what ends up happening is just that. We are going to have an acceleration in the direction of wherever the force is going. Yeah, these aren't balanced forces. They're both heading this way. So that's the direction of the acceleration. So once more, this results in a net force of twice what each of them are doing, right? We're going to do some more work with that later and talking about net forces and stuff like that, how that works out. Okay, so let's try some examples here using the F equals ma formula. So here's our formula right here. We're going to rank the following objects in order of the magnitude of the net force exerted on the object. So remember, magnitude means we do not care about the sign, right? Direction is the sign. Positive or negative tells me which direction I'm going. So we are just looking at the literal magnitude. So let's go ahead and I'm going to kind of give you some time to try these. I'll do the first one, and then you guys are going to try the next three. And then you are going to rank them in order from greatest to smallest. So let's do this first one. We're talking about, again, that force equals ma. We have a 1,250 kilogram automobile gaining speed. That means we have an acceleration, and look, those units are the units of acceleration. If I am gaining speed, there is an acceleration. So what's the force acting on this object? Force equals my mass, 1250, times my acceleration times 2. So let's see what we get here. I should be able to do this, 2,500. So this is the magnitude of the force is 2,500. What's the units again for force? Newtons. Now what this means, guys, again, because you've all driven in cars before, you know that when the car is not accelerating, it just feels like you're just kind of sitting, right? It feels like you're sitting still, yeah? If your car is on cruise control, it feels like you're sitting still. That's because there's no force actually acting on you because there's no acceleration. If a car is gaining speed, that's when you start to feel this like, wah, going back into your seat because you are accelerating. So you feel that force, right? That's literally why you feel that force, because you are accelerating. I'm going to go ahead and do B with you to compare these two, actually, and then you're going to try C and D. So same thing, we're going to find the force acting on this airliner. Force equals MA. We've got a 200,000 kilogram airliner flying in a straight line at a constant 280 meters per second. That is not the acceleration because it says meters per second. This is the velocity. This was the acceleration up here because it was meters per second squared, but this is the velocity. And here's the important thing we have to realize. If it is a constant 280 meters per second, this airliner is on cruise control. When your car or when the airplane is on cruise control, do you feel any force on you? No, and that's because if my velocity is constant, I have no acceleration. Again, a lot of you guys are really confused thinking that a constant velocity means constant acceleration. No. If my velocity is not changing, I do not have an acceleration. So, therefore, there are no forces acting on you. This is literally why you can go up and ride in a plane. And yeah, in the beginning you're like, whoa, as it accelerates. But once it reaches its cruising speed, you don't feel anything. You can walk around like totally normal, right? That's literally why. If you have a constant speed, there is no force acting on you. No net force. That is a very important thing I need to make sure I emphasize because that's going to matter later. So go ahead and try the next two, and then go ahead and rank them in order of their magnitudes from greatest to least. Okay, let's try these. So we got force equals MA. We got a 500 whatever kilogram chuck. Slowing down, that's an acceleration, as well as right here, meters per second squared. That is an acceleration. Now, I know it says slowing down, but because we don't care about the direction, right? We just said we care about the magnitude. We don't need to make this a negative. We're going to go ahead and just put 0.6 because we only care about the magnitude. So 4,500 times 0.6 is 2,700 newtons of force you're feeling. And again, though, that is slowing down. So yes, it's going to be this kind of thing. Or when you slow down, you kind of come forward. When you're speeding up, you're getting pushed backward. But that's the magnitude of the force. It would be a different direction, though, than gaining speed. And the last one, a 80 kilogram hiker climbing up at a 4-degree slope at a constant 1.2 meters per second. So force equals MA. My mass is 80. Climbing up at a 4-degree slope, that doesn't matter, that's fine. We're just climbing this like mountain at a constant velocity. A equals 0. So you should have gotten, there's also no force they're feeling. They're just walking up nice and slow, constant velocity. So ranking these, we can see, obviously, that this is the greatest magnitude, this is the second greatest, and then these two are tied for third place. So in both of these cases, that's 0 newtons, guys, not on. 0 newtons in both those cases, right? They're not going to feel any force on their body because they're not accelerating. It will almost feel like they aren't moving. And again, hopefully you can understand that and relate that to driving in a car. There are times when you are driving in a car when it feels like you're not moving, and then other times when you're glued to the back of your seat. This is no net force versus, yes, there is a net force. Okay, last question we're going to talk about, and then you guys are going to watch another little video to take some notes on the types of forces that we're going to be working with, is again, just one more time, working with this force formula and how we can use it. So it says, the bodybuilder exerts a force of 300 newtons to lift a 50 kilogram barbell. So that's mass. What is the acceleration of the barbell upward? So he's going like this. We want to know how quickly that object is going to accelerate. So what is the acceleration? So there's all of our variables. We know the force he's having to exert to lift it. We know the mass of the barbell, and then we're going to be able to find the acceleration. And how do we do that? Well, we know force equals mass times acceleration. I've got 300 newtons for my force. I've got a mass of 50 kilograms, and I'm trying to find A. So pretty simple, right? This is a very easy question. All I got to do to solve for A is divide by 50. So this is going to result in a pretty quick acceleration. I think I just made these numbers up. What would the acceleration be? 300 divided by 50. Yeah, 6 meters per second squared. That's 300 divided by 50. Yeah, this guy is just like, this is so easy, and just like yanks it up. That's good. That's actually going to accelerate pretty fast. Okay, so try it one more time. Same thing, we're using the force equals mass times acceleration. Look at what we're trying to solve for. Look at what we have. Go ahead and give this a shot to solve this question. Okay, let's see. A child pulls a small car toy with a force, F, of 5 Newton, resulting in an acceleration, A, of 1 meters per second. What is the mass of the car? So same thing, we're just using F equals ma. We've got our force is 5 newtons. We've got mass, we don't know. And our acceleration is 1. Now, hopefully you could have seen right here, oh, I know what m is, but just so we understand. Divide by 1. My mass is going to be 5 kilograms for this car. Okay, so I'm going to tell you what you're going to do from here. Oh, actually, I'm going to do one more thing, and then I'll tell you what we're going to do from here. So just a little history onto forces. Before you guys watch another video focusing on specifically the type of forces we're doing, you do not need to copy this down. I'm just going to talk through this, and then you're done with this video. So once again, we said that the measurement for forces is a Newton. Isaac Newton, super important dude. He discovered calculus, although that's kind of controversial as well because there was somebody else in a different country who discovered calculus at almost the same time. But us in America here, we typically give the credit to Isaac Newton. And he did a lot of work with physics. And again, that makes sense. I've talked to you guys. Physics and calculus go hand in hand. Yeah. Now, he wrote his 3 laws of motion, as well as the universal law of gravitation. We're going to learn that later. It's a formula, actually, that figures out how to calculate the acceleration due to gravity on any planet or anywhere. There's a way to do it. And he lived from 1643 to 1727. So he wrote those 3 laws of motions, tons of stuff about calculus, and this as well. Because of all the stuff he did, that's why the units of forces are named for him, newtons, because of so much of what he did was so important. So all of these different types of forces here, do not copy this down, you don't need this right now, are measured in newtons. We have the force of friction, we're going to learn later. Gravity, magnetic, applied, like if I'm actually touching something. Buoyancy, if you're floating in water, that's a force actually. Tension is when you're pulling on something. Drag, again, that's going to actually be a contact force because that's you in contact with the air. That is a contact force because air is a physical object, right? Versus gravity is not, yeah. Springs, we can talk about springs later as well, like a slinky, yeah, or just a spring. And the normal force is something we are going to learn later. So these are all the different types of forces. Again, like we said, we have contact forces, meaning you actually have to touch. Non-contact forces, again, magnetic, electric, and gravitational. Those are things that are not touching, they're not physical, yeah, they're created by fields. So from here, you are going to stop watching this video. You are going to watch this next video and take notes on the 5 different kinds of forces we're going to be focusing on. So I'm going to give you a second to copy these 5 down, although I mean it's going to be in the video. We have applied force, gravitational force, normal force, frictional force, and tension force. If you want to write those down first, you can, but you'll see them all in the video. You're going to watch this, take some notes, and then we're going to come back and talk a little bit more about these things. Make sure we got this understood.